Okay, so moving on. We've got allyl bromide is used in the production of polymers. Part is of the double bond is a pi bond. Draw a labeled diagram to show the formation of a pi bond. Okay, so hopefully this one isn't too bad. You've got your carbon sigma framework. You've then got your two p orbitals there. So you need to label those up, p orbitals, and they will overlap to give you your pi bond above and below. So again, label this up, pi bond, and you may want to state the p orbitals overlap above and below the carbon sigma bond to give you a pi bond. Okie dokie, so what is meant by a homologous series? You've got the same functional group with each successive member differing by CH2. What is the general formula of the homologous series that has allyl bromide as a member? So let's have a look. Our formula is C3H5Br. So it looks to me that we have got CnH2n minus 1 Br would work for that one. Give the systematic name for allyl bromide. Let's go back and have a look at him. So there he is. You've got 1, 2, 3 carbons there. So it's going to be propene. Shall we draw him out? I've got 1, 2, 3, and then I've got a Br coming off there. The rest are going to be H's. So I've got propene, 3 carbons, prop 1e is going to be your carbon backbone. If that's carbon number 1, that's going to be carbon number 3. So it would be 3 bromo prop 1ene. Reaction mechanism uses curly arrows, which can involve electrophiles and nucleophiles. What does a curly arrow represent? Obviously, a curly arrow represents a movement of an electron pair. What is meant by the term nucleophile? A nucleophile is an electron pair donor. Okay, so we now need to do a mechanism reacting with sodium hydroxide. So if you have your hydroxide here, pop your lone pair on. This bond is obviously polar because bromine is going to be more electronegative than carbon. So here he comes, whee, into carbon there. It means that bond has got to break there. And I replace the bromine with hydroxide. The rest stays the same, so that's CH2, and then I have 2 H's coming off, and obviously I'm also going to make my Br minus ion, like so. Name the type of mechanism. That is, of course, nucleophilic substitution. It's substitution because I replace my bromine with OH. And this boy is going to be a nucleophile because he's attracted to the delta plus carbon. Okay, it's now going to turn its attention to the carbon-carbon double bond, and it wants me to react it with bromine. So pop your bromine molecule on like that. That is going to have delta plus and delta minus as he attracts the double bond. Electrons come out of the double bond to form a bond to that bromine. That means that bond has got to break. That gives me this intermediate. Like so. And that's the bond that I've made. And then Br minus, like so, comes in and pops onto that carbon with the positive charge there to give you my final product where I've added bromine across the bond, like so. And that mechanism is, of course, electrophilic addition. This is going to be an electrophile because it's attracting a double bond, and I've added bromine to that molecule across the double bond. Right, okay, so carrying on. We're now reacting through this sequence now, a couple of steps. State the reagents and conditions for step 1. Well, I'm removing the double bond, adding hydrogen, so of course it's hydrogen with a nickel catalyst. In step 2, 1-bromopropane reacts with chlorine by free radical substitution. Outline that mechanism. Okay, so here we go. You know that we have initiation, first of all, and that uses UV light. My chlorine molecule breaks up to give me 2 chlorine free radicals, and you can always put UV light on there just so that you, okay, that is your essential condition, UV light, so best do that. You've then got your propagation. In propagation, you've got C3H7Br is going to meet up with one of those chlorine free radicals. That is going to whip off a hydrogen to give me C3H6Br plus HCl. Then that boy is a free radical, so I want C3H6Br plus Cl2 is going to give me one of my products, C3H6BrCl, and another chlorine free radical. Termination steps, you've got various termination steps you can use. Probably the most common is going to add, you've got your C3H6Br free radical, meets up with your chlorine free radical to give you your product again. Equally, you could have all termination steps. So I could have 2 chlorine free radicals coming together to give me Cl2. Equally, I could have 2 C3H6Br free radicals coming together to give me C6H12Br2 as well. Okay, free radical substitution produces a mixture of organic products. 2 reasons why. Well, you can have further substitution of your product of C3H6BrCl. That can carry on reacting to give you further substitution reaction. And also the substitution can occur at different parts of the chain. You don't know which hydrogen is actually being replaced. We just put C3H6BrCl. You don't know which hydrogen that Cl is actually replaced. So substitution can occur at different parts of the chain, and also further substitution can occur after you've made your product.